Got Arlene Fiore. She is a associate professor in the Department of Earth and Environmental Sciences in Lamont Doherty Earth Observatory of Columbia University and an international expert in how regional air pollutants interact with global atmospheric chemistry and climate. In over 50 published peer-reviewed papers, Arlene has contributed to understanding of atmospheric chemistry, ozone pollution, the global roles of methane in air quality and climate, the role of intercontinental transport and regional air quality, and global environmental policy analysis. A 2011 recipient of the American Geophysical Union's prestigious James B. McIlwain Medal, is that pronounced right? She holds a PhD in Earth and Planetary Sciences from Harvard University. So I'd like to welcome Arlene.
And thank you so much, Bart, for getting our panel organized. It's been really fun to have the opportunity to interact with the other panelists and Bart in preparation for today. And also, I just want to say how excited I am to be here for this, this conference and to have the opportunity to share with you a bit about my perspective on regional to global scale processes that are relevant for attaining the new U.S. ozone NAAQS. And I see Tracy standing at the back, so I'll take this opportunity to thank her for putting this together. I also wanted to acknowledge my team back at Lamont, but in particular, 3 individuals, Luc Valin, who's a postdoctoral researcher in my group, Harold Rieder, who was a postdoctoral researcher and has now gone on to a faculty position at University of Graz in Austria, as well as a colleague, Lach Lamsel from NASA Goddard Space Flight Center, who works closely with Brian Duncan, who's on the next panel. All 3 of those individuals have created plots specifically for this talk that are unpublished. So I wanted to acknowledge that, and of course also our funders. And so we'll start out with just a very, very basic overview of ozone formation. And so what I'm showing here, if we focus first on non-methane VOCs, so these are non-methane volatile organic compounds, and nitrogen oxides, in the presence of sunlight, react to form ozone. And one of the things that makes the ozone attainment of the standard so challenging and just improving air quality for ozone and why it's been a persistent issue for decades is that there's a diverse array of sources that contribute to ozone production that include both natural as well as anthropogenic. So even if we were to turn off all sources associated with human activity, we would still have some natural levels of ozone present in the atmosphere. And these little schematics here are just intended to illustrate that some of the different sources, but they're not exhaustive. And so our non-methane VOCs, there's a whole class of compounds, some of which are very highly reactive. And so on timescales of hours to days, they contribute to the local to regional scale ozone episodes. And so these are the compounds that are regulated to attain compliance with the NAAQS. I like to also point out, though, that methane is a VOC that reacts on a much, much slower time scale. A typical molecule of methane, when emitted, will stay around in the atmosphere for an order of a decade or so. But that methane, in the same way, can also react in the presence of NOx and sunlight to form ozone. And so this contributes to what we can think of as sort of a background level of ozone. Okay, and so when we are actually measuring ozone, we don't know where that specific molecules of ozone that we're measuring come from, but the total ozone concentration and surface area is going to be some that are considered part of the background, where here I mean ozone that's not produced from U.S. anthropogenic emissions, and some of it will be produced from those anthropogenic emissions within the U.S. So a little bit of historical context, very, very broad overview, but to point out that our ozone abatement strategies have evolved over time with our understanding of the ozone smog problem. And so back in the mid-20th century, ozone smog was kind of recognized as an urban scale problem, with Los Angeles the poster child for smog. And the mechanism was recognized that it was non-methane VOCs and NOx reacting in the presence of sunlight. And for the case of urban smog in Los Angeles, going after the large source of anthropogenic non-methane VOCs was very effective at reducing the highest ozone smog events. However, in the 1980s, it was recognized that in the eastern US, for instance, there was a regional character to this ozone smog issue. And when that same strategy was applied in the eastern US, there wasn't much response in ozone. And by the late 1980s, it was recognized that there were these natural hydrocarbon emissions, in particular isoprene, coming from vegetation, broadleaf vegetation in the eastern US, that isoprene is a very, very fast-reacting hydrocarbon. And so going after the sort of longer-lived, in many cases, non-methane VOCs in the eastern US was not effective. And it really shifted the paradigm of ozone control strategies to one of reducing nitrogen oxides. And so I'd say around the turn of the century and into the present, it's been recognized that there's this urban portion of the problem, a regional scale portion of the problem, but also a hemispheric and global scale of ozone transport. And so it's been now established that ozone can be transported from one continent to another, and the role of this background, particularly as we think about attaining standards that are becoming lower, has been receiving a lot of attention. And so I put here methane with question marks, in that we don't regulate methane from an air pollutant perspective, but we are now starting to regulate it, as we were just hearing this morning, as a greenhouse gas. And so there's a co-benefit here coming from greenhouse gas controls on methane that will help to reduce kind of hemispheric and global scale background ozone levels. Okay. So this map attempts to show the implications of setting the NAAQS at different levels. And what I want, the red dots tend to jump out, but that's not what I want you to focus on here. So if we look at the dark blue dots, those are the ozone design values, which Rob nicely explained how those design values are calculated. This is using 2011 to 2013 data. So these aren't actually the years that will be used for formal regulatory process, but it nevertheless gives an idea. So the dark blue are monitors that were in exceedance of the 75 ppb standard, and the light blue dots now show additional monitors that are in exceedance with this new 70 ppb standard. So we can see that there's an expansion of this potential non-attainment region. And if we look in Wisconsin, we see this kind of movement inland from the lakeshore monitors. Okay, so while this poses challenges, I really want to emphasize that air quality has been improving dramatically in the United States. And one way that we can document that is from decade-long satellite instruments, such as this one that measures tropospheric NO2. So NO2 is part of NOx, which is the precursor to ozone. And so we see, if we look at 2005 versus 2014, the warmer colors indicate higher values, and we see this reduction in NO2 in the troposphere, which is primarily in the boundary layer. And I also wanted to highlight a website for those of you interested in looking at your city or your region that NASA has put out of air quality from space. And so I encourage you to check that out if you're interested. Now, in my group, we've been using these NO2 columns not just to look nationally, but also to zoom in over, in the example that I'll show today, it's kind of the New York City metropolitan area region, the tri-state area. And we're also looking not just at long-term trends, but at information that we can glean from weekly cycles in NO2 emissions. And so this weekly cycle is thought to largely come about because of changes in diesel NOx, in particular truck driving patterns, that there's lower diesel NOx emissions on weekends than during the weekday. And so what this figure is showing is for the mid-2000s, the weekday NO2 columns versus the weekend NO2 columns. And we see it's about a 35% decrease averaged over this region here from the weekday to weekend. And now what we've been looking at is how that's changing over time as NOx emissions have been decreasing, including due to controls on diesel engines. And what we see is that by the early 2010s, the weekdays now look a lot more, they're still a little bit higher, but a lot more like the weekends used to look in the mid-2000s. And we see that the weekends are even lower. And so we can then ask, what are the implications for surface ozone if we look weekday versus weekend? And so this plot is now showing the 90th percentile summer afternoon surface ozone concentrations for this same region. So these are the AQS, the Air Quality System EPA monitoring sites. And we see that if we look at the regional scale, there are decreases in ozone that occur from weekday to the weekend, and we see some declines happening in the early 2010s. In particular, we see that the weekends are now a lot cleaner. And so we draw two conclusions from this. The first is that additional controls on diesel engines that reduce NOx would help to lower weekday surface ozone, as well as the tropospheric NO2 columns. And it also implies that this region is sensitive to NOx emissions, which tells us that if we continue to reduce NOx, we should see additional reductions in ozone. In my research group, we also use global chemistry climate models, which are basically climate models that we put the chemistry that we need to calculate air pollutant distributions in on top of this. And we do this at a global scale. And so we've been thinking a lot about how we can use these models to answer questions like, what does a particular set of assumptions about future emissions and potentially future climate change mean for at the monitor level? And so the way we're doing this is trying to tap the global models for what we think they're best at, which is kind of broad scale, average regional changes. And so for the example I'm going to show you, we're looking at the northeastern quadrant of the US and kind of calling that one region, constructing a distribution of ozone concentrations from present day to a future time period that we're going to look at 2021 to 2025, and taking the change that the model projects at each percentile of the distribution and adding that on to the present day observed distribution at monitoring sites. And so what I'm showing here are the observed number of days above 70 ppb, so this is the daily max 8-hour metric. And these are the CASNet, the Cleaner Status and Trends Network of monitoring sites. And we're looking at our base period as 2001 to 2005 to kind of match with the modeling that we had done. And so we see that many sites are showing an average number of days for a summer that are above kind of the 4 to 6 ballpark, which is telling us that these sites are probably having trouble with achieving a 70 ppb standard. When we then go into the future, using an emission scenario that has a 40% decrease in eastern US regional NOx emissions, as well as projected changes kind of globally, and potentially it's including climate change as well. But the interpretation that we have is that the bulk of what we're seeing is really driven by these regional NOx emission reductions in the model. And so we see that the good news is that by 2021 to 2025, under this particular scenario, we see that most of the sites, except for 5 of them, now have 3 or fewer days above 70 ppb. And so standing in Wisconsin and showing this map, I'm sure you're all noticing this gaping white space over Wisconsin, and this was because there is a CASNet site in Wisconsin, but it didn't have enough data capture during 2001 to 2005. So what Harold kindly did, Harold Reeder, took an AQS site in Wisconsin that had year-round monitoring, which was a Dodge County site, so somewhere in this box here. And if we look first at the observations of this site for 2001 to 2005, we're looking at the 70 ppb standard in red and the old 75 ppb standard in blue. And so what you see is just looking at the observations at that site, it looks like moving from 75 to 70 ppb would double the number of days above that NAAQS level, including not just in summertime, but also in spring and fall. However, under this future projection that we're doing with this model that has about a 40% NOx reduction over the eastern United States, we find that it looks like that site should be able to have an easier time meeting a 70 ppb standard. So it suggests that attainment of this standard is possible with continued NOx reductions. So in the next slide, I've taken this from a book chapter led by Terry Keating, who's one of the panelists on the next session. And he has this chart that basically breaks total surface ozone concentration into portions due to regional emissions, local emissions, as well as hemispheric background. And if we move from the historical bar chart into some future bar chart, what you'll notice is that due to our efforts to control local and regional ozone pollution, those portions are declining. In this particular future, the assumption is that that hemispheric background is rising, which we might expect to occur from global increases in NOx and methane. And you'll note here that Terry had envisioned that standard might be lowered, as just happened. And one way to think about it is it's getting harder and harder to reduce our regional and local portions as we kind of make those chunks smaller, and of course we'll continue to work on them, but we might also want to take this alternate view where that bar flips over and we think about starting to reduce that hemispheric background. And so as I've mentioned earlier, one way to do that is to consider lowering global methane abundances. And this is just one result from a multi-model study that was coordinated by the Task Force on Hemispheric Transport of Air Pollution that Terry Keating co-chairs, along with Frank Dentiner from JRC in Italy. And this is showing that across a whole suite of international modeling groups, that the results are pretty consistent, that a 25% decrease in global anthropogenic methane emissions would lower this hemispheric background over northern mid-latitude regions by about a ppb. And that brings with it, of course, benefits for health as well as agriculture. And in addition, a co-benefit to methane reductions, of course, is that methane is a potent greenhouse gas, as is the ozone that's produced during its chemical destruction in the atmosphere. And so the estimate here is that this same decrease in anthropogenic methane emissions would be associated with about a little less than 0.3 of a degree of global mean avoided warming by 2050. Okay, so this is just one part of that background ozone that I mentioned earlier. And so in this slide, what I'm showing is an estimate actually from my PhD work where we turned off North American anthropogenic emissions in a model and looked at the distribution of background ozone. And what we found is this is a summertime. The model run was done for summer of 1995, but the background is higher in the western United States, particularly at high altitude regions. And it's also, this is results from another study that we did, and I'd like you to focus on this green line here, which is showing the model estimated background contribution to surface ozone over the northeastern quadrant of the United States. And we see that it's higher in springtime and declines into summer. And so there has been a lot of work on background ozone over the last decade or so since this work was done. And the latest background estimates use higher resolution models. They look at different years. But these general findings that the background is highest at high altitude sites in the western US and generally higher in spring generally are pretty robust across these studies. And I would say that the research emphasis has moved a bit and now is very much focused on these episodic background events that can potentially contribute to pushing a monitor over the NAAQS level. And so in this slide, I wanted to sort of put that in context that we've had, as we're all aware, this decline in the NAAQS level over time. There's also been a change in the formulation of the standard, in that the 1979 standard was a 1-hour average, and in 97 that was changed to an 8-hour average. Model estimates, roughly in terms of an average sense, will say that the background is 15 to approximately 40 ppb. And I like to think about that space in between as kind of this cushion of ozone that's allowed to be produced from US anthropogenic emissions. And of course, as those red bars kind of become lower here, and if the background rises at all, that cushion thins and can pose challenges for attaining the standard. And with respect to these episodic events, I'm just showing kind of a range here from some work that I was involved with that looked at Asian pollution influence in the western United States, as well as stratospheric intrusions over the high altitude western United States. And there were events that we found that can push awfully close to the 70 ppb level. And so a challenge then becomes, how do you identify these events and attribute them to a kind of non-controllable source as opposed to anthropogenic emissions? And so I coordinated an article that was published in Environmental Manager as part of NASA's Air Quality Applied Sciences team special issue back in 2014. And what we tried to do in that paper was to look across the range of published estimates for ozone produced from wildfires, as well as ozone intruding from the lower stratosphere into the lower free troposphere and surface air, particularly over the western United States in springtime. And so this is just a bar chart showing the kind of range of estimates that have been out there in terms of those contributions. And this article goes through showing some examples of cases where satellite data, in situ measurements, and models have been combined to detect and attribute these events. And so this is an example out of Russ Dickerson's group. He's at University of Maryland. And there was an episode in the summer of 2002 when Canadian wildfires, you can kind of see the smoke plume here coming down. This is basically reaching the mid-Atlantic and led to exceedances of both PM and ozone in Maryland. And then this is an example from my co-investigator on NASA's Air Quality Applied Sciences team, Mei-Yoon Lin at NOAA GFDL and Princeton University. Her work on stratospheric intrusions at high altitude sites in the western United States. And so this is, I think, a real challenge, particularly for the western US, trying to detect and attribute these natural events. And Brad Pierce, who's in the audience, has actually led some work for getting helping to get together a stratospheric intrusion event to be classified as an exceptional event for the state of Wyoming. So one final challenge before I wrap up here is climate change. And so the big question is, to what extent will warmer temperatures worsen ozone pollution in places that are currently polluted? And the rationale for thinking that this is a problem is decades of research and observations that show that there's this really strong correlation in polluted regions between temperature and surface ozone. And so this is just one example from a site in Pennsylvania where ozone, this is a July mean daily max 8-hour ozone shown in black. We're looking from 88, which was a hot year, in the Northeast, through 2014. And the red is showing the July mean daily maximum temperature. And so what we see is the wiggles generally go up and down together, which suggests that a warmer summer is going to lead to more ozone being produced, and there's kind of mechanistic reasons behind that. But we also notice this sharp downward trend in the black line, the ozone concentrations. And so this speaks to the success of our NOx emission controls that have been implemented kind of starting in the late 90s and continuing to be implemented through the present. And I'd like to call your attention to this period in kind of 2010, 2011, 2012, where temperatures were similarly hot as in 1988, but we see that the ozone levels are roughly 20 ppb lower now. And so this tells us that the NOx emission reductions, things we've already been doing, are helping to guard against any worsening in ozone pollution that would be brought about from warming climate. And so continuing NOx emission controls should help to further protect us from climate change in polluted regions, meaning the ozone increase associated with warming due to climate change. Okay, so my final slide here are basically the kind of what I'd like you to take away from this regional to global perspective on attaining the U.S. ozone NAAQS. And so the first bullet is really the key point that NOx emission reductions have been successful and should continue to be successful in moving towards attainment of this lower NAAQS level. I'd also like to just emphasize that background contributions, it's not just one number. It varies in space and time, and it's higher at high altitude, which is why the western U.S. at altitude is particularly susceptible to high background. Exceptional events, I think there's a discussion kind of out there about the extent to which we can continue to call them exceptional if particularly with wildfires increasing as it's becoming hotter and drier in the western U.S., and also as that level which we're measuring these events with respect to is becoming tighter. And from what I understand, it's a lot of work to put together an exceptional event declaration. And so developing infrastructure, I think, to identify these events and also determine how frequently they are happening and to the extent to which they really do pose a challenge to attaining a 70 ppb standard, I think is a discussion point. Sort of alluding to the next panel, one of the next panels is that transboundary transport, this global perspective on ozone pollution. If global emissions are to rise, then that could increase the boundary transport coming into the U.S. And just to leave with the idea that there is this co-benefit with climate reductions of methane that should help to lower background ozone produced through methane oxidation in the atmosphere. So thanks for your attention, and I'll move on to